Okay, hello everyone in a new video. So we have reached part 2 of chapter 3, which is the chapter of electric current for grade 10 students. So now in this part we are going to solve some exercises and complete the explanation of this chapter. So we are in exercise number 2. Five electric dipoles are connected to a generator as shown in the adjacent figure. So here what's meant by dipole? So we know that pole is a terminal. So consider the following electric component. Di stands for 2. So this electric component is said to be a dipole because simply it has two terminals. Are connected to a generator as shown in the adjacent figure. We have that I2 is equal to 2I3 is equal to 4 amperes, which means that the value of I2 is equal to 4 amperes. And 2I3 is equal to 4 amperes, which means that the value of I3 is simply equal to 2 amperes. And I4 is equal to 1 amperes. And as we have said previously, that the trick in solving such type of exercises is to label the traverse current and the applied voltage on the electric circuit itself. Then here let me say that the value of I1 is equal to, we don't have the value of I1, we have the value of I2, which is equal to 4 amperes. We have the value of I3, which is equal to 2 amperes. And I4 is equal to 1 amperes. Now number 1, they are telling me determine the missing currents in the circuit. So first we need to specify the missing currents. So the missing currents are given by I1, by I, and by I5. So notice that we have three unknowns. In order to determine these three unknowns, we need to apply the law of addition of currents 3 times, because each law of addition of currents will lead to a linear equation. Okay, so and the order that we proceed is very important. Suppose in this case we need to start by determining I. So notice that in this case, if we need to apply the law of addition of currents at this point, so notice that we have two unknowns. We cannot determine I and I1 simultaneously. Now moreover, we can start by applying the law of addition of currents at the point B, because we know the value of I3 and we know the value of I4, then we can determine the value of I1. So let's start by apply law of addition of currents, and here we need to specify the node that we are applying the law of addition of currents, at which we are applying the law. So we have several nodes. We have node A, we have node B, and we have node C. Notice that S, M, and D, they represent a node, but we don't benefit anything from applying the law of addition of currents, because simply we have two branches connected to this node. So we can always make the use of the law of addition of currents by applying this law to a node in which 2 or more branches, 3 or more branches are connected to this node. So here we need to specify the node to which we are applying this law. So let's say apply law of addition of currents at node B. And this law is given by summation of I in is equal to summation of I out. Then on the left hand side of this equation we will write the currents that are entering the node, and on the right hand side of this equation we will write the currents that are leaving the node. So referring to this node, notice that only the current I1 is entering the node, so this is I1, and the currents that are leaving the node are given by I4 and I3. So this is equal to I4 plus I3. And notice that in this case we are interested in determining the value of I1. So what's the type of this equation? This is a linear equation in one unknown. The unknown is I1. So it is kept as a variable which is equal to I4 which is equal to 1 plus I3 which is equal to 2, so this is 3 amperes. Then I1 is equal to 3 amperes. Now, as I have said previously, that the trick in solving such type of exercises is to label the current on the electric circuit itself. Here we have that the value of I1 is equal to 3 amperes. And indeed, notice that I1 reaches the point B and splits into two currents such that the summation of this current is equal to the main current or the initial current, which is I1. Now, if this is I3, then this is also I3 which is equal to 2 amperes, and this is also I2 which is equal to 4 amperes. And here, sorry, so this is also I4. So notice that now we can determine the value of I5 because at the node C we have three currents that are entering and we know the values given by 4, 2 amperes and 1 amperes. Across the terminals of D3, the value of the traverse current is I3 is equal to 2 amperes. As for D4 is given by 1 ampere. Okay, so we can determine the value of I5. And at the same time, we can determine the value of I from the node A because notice that I splits into two current given by 3 and 4 amperes. Moreover, the value of I must be equal to the value of I5 because notice that from C to A, this is a branch consisting of two electric components that are in series, then they will be traversed by the same current. Therefore, I is equal to I5. So first, let's calculate the value of I. Then we can mention the law of uniqueness of currents and say that I is equal to I5 since the battery and D5 are in series. So let's say apply law of addition of currents at node A. So always it's important to mention the node to which we are applying this law, and let's say summation of I in is equal to summation of I out. On the left hand side we write the currents that are entering the node and they are given by I, and on the right hand side we write the currents that are leaving the node that are given by I1 plus I2. And notice that in this case the unknown current is I1 we have determined previously, which is given by 3, and I2 is given by 4. The type of this equation is a linear equation of non-unknown. The unknown is I, so this is equal to 7 amperes. Then the value of I is equal to 7 amperes. And then the trick is to label the current on the electric circuit itself. Now it's left to determine the missing current I5. So as we have said previously that I5 represents the current traverse across the terminals of D5 and I represents the current traverse across the terminals of the generator. So we can say, so let's give the generator the name G and D5 are in series. According to the law of uniqueness of currents, they are traversed by the same current. So in this case, I is equal to I5 is equal to 7 amperes. So the value of I5 is equal to 7 amperes. And notice that if you apply the law of addition of currents at the node C, we have that 4 plus 2 plus 1, this is equal to 7, which is I5, okay? Now in number 2 of this exercise, they are telling me a load D6 is connected in parallel to D4. Let's connect this load. So this is D6. This is D6. So D6 is connected in parallel with D4, so that the current I1 is increased by 0.5 amperes. Now notice that the moment we add an electric component to the circuit, all the values of the currents will change. So let's erase all the values of the electric currents. So everything in the circuit will change except for the voltage of the battery, and they didn't specify the voltage of the battery. So in this case, they are telling me that I1 increases. Let me say that I1 is equal to 3 amperes. So the values of the currents will change. And they are telling me that I1 is increased by 0.5 amperes. So previously I1 is equal to 3 amperes. So it increases by 0.5 amperes, which means that the new I1 is given by 3 plus 0.5, which is equal to 3 amperes, 3.5 amperes. So we have that the new value of the electric current corresponding for the new circuit under this change is given by 3.5 amperes. And they are telling me an analog ammeter of dial 150 divisions. We have the D, 150 divisions, with non-centered needle is connected in the branch BM. Then here we have an ammeter. Okay. Now in part A, calculate the current traversing D3, knowing that the needle deviates 75 divisions. So small d is equal to 75 divisions under a scale of, this is wrong, it must be 2 amperes. And we have that the scale S is equal to 2 amperes. So we are interested in determining the value of I3. So notice that in order to determine the value of I3, we need to apply the law of addition of currents at the point B, and moreover we need to determine the value of I1 and the value of I4. Already we know the value of I1, which is given by 3.5 amperes. It's left to determine the value of I4. I4 can be determined from the reading of the analog voltmeter, ammeter. So first we need to determine the reading of the ammeter. Then using this reading we can determine the value of I3 by applying the law of addition of currents at node B. So the current I, under which the ammeter is reading, is given by S multiplied by small d divided by capital D. Notice that we are interested in determining the value of I, which is in this case given by I4. Now the scale is given by 2 multiplied by 75 divided by capital D, which is given by 150. So this is equal to 1, since everything is expressed in the SI, so the value of I4 will be in the SI. So I4 is equal to 1 amperes. Now after we have determined the value of I4, which is being read by the ammeter, now we are ready to apply the law of addition of currents at node B in order to determine I3, because it's the only unknown. And here we suppose also that the direction of the current I4 is from B to M. So adding the load D6 will not change the direction of the electric current. Okay. Now let's say apply law of addition of currents at node B, then we have that summation of I in is equal to summation of I out. On the left hand side we write the currents that are entering the node B, which is given by I1, and on the right hand side we write the currents that are leaving the node B, which is given by I4 plus I3. Knowing that we are interested in determining of I3, what's the type of this equation? Linear equation and one unknown. So I1, which is equal to 3.5, is equal to I4, which is equal to 1 plus I3. Then I3 is given by 3.5 minus 1, which is equal to 2.5 amperes. So the value of I3 is equal to 2.5 amperes. Okay. And the trick in solving such type of exercises is to label the electric current on the circuit itself. Now yet I didn't explain part B, but let me solve it, and in the coming section I will directly explain part B. So now in part B, they are telling me determine the currents traversing D4 and D6, knowing they are identical. So we are interested in determining the electric currents. So let's say that this is I4 prime, and this is I6. We are interested in determining the value of I prime 4 and I6, knowing that they are identical. So let's say since D4 and D6 are identical, then they are traversed by the same current. So here we are saying that since D4 and D6 are identical, then they are traversed by the same current. So notice that now we need to translate this statement into a mathematical formulation. So they have the same current. What's the current traversing D4 is given by I prime 4, which is the current traversing D6, which is given by I6. Now notice that the main current, the initial current, which is given by I4, at the point M, it splits into two currents, and they are given by I prime 4 and I6, and the number of components is 2. So in this case we have that I4 divided by the number of components, which is 2, which is equal to 1 divided by 2, which is equal to 0.5 amperes. Then I prime 4 is equal to 0.5 amperes, and I6 is equal to 0.5 amperes, because these electric components are identical and they are in parallel. And this makes us move to the next section, which is identical components in parallel. So we are in section number 5. So suppose that in this case we have two identical components in parallel. And suppose that this is the node A and this is the node B. This is the electric component D1 and this is the electric component D2. And suppose that the main branch is being traversed by the current I, and at the point A it splits into two currents that are given by I1 and I2. So in this case we know that I is equal to I1 plus I2 according to the law of addition of currents. But moreover, because the two components D1 and D2 are identical, then we say since D1 and D2 are identical, then they are traversed by the same current. So we have that I is equal to, so what does it mean that they are traversed by the same current? That the current of D1 is equal to the current of D2 translated into the mathematical formulation, which is equal to the main current given at the point A, which is I, divided by the number of components that we have that are given by 2. So in this case, if you know the value of I, we can determine I1 and I2. Now what happens if you add another component D3 that is in parallel and also identical? So this is I3. And then in this case, we say that I1 is equal to I2 is equal to I3 is equal to the main current divided by the number of components that we have, and this is given by 3. Okay, so always this factor here represents the number of electric components in parallel that we have. So notice that in case of the law of addition of voltages, the electric components said to be in series, connected in series, because the law of addition of voltages in that case, in the case of voltages, is concerned about series grouping, whereas in the case of current, we know that the current is additive in parallel grouping. For this reason, in this case, the grouping is parallel. Now let's move to the other section, which is section number 6, parameters across the ammeter and the voltmeter. So suppose here, so this is idea number 1. Suppose here we have an ammeter. Now notice that previously I didn't specify here the COM terminal, but for example, if we are interested in the positive reading, so this is the positive pole, this is the positive pole, this is the negative pole, then the COM terminal is connected to the negative pole. Okay, so suppose that this is the COM terminal and this is the point A. Say for example this is the point C and this is the point D. We know that the voltage across an ammeter is 0, since it is of negligible resistance. Now the resistance, we will cover the resistance in the next chapter, which is chapter number 4. So in this case, UCD is equal to 0 because the ammeter is of negligible resistance. This is the point C and this is the point D. Now what about the voltmeter? Is there a similar statement for the case of voltmeter? And the answer is yes. So suppose that this is the voltmeter and this is the COM terminal. So in the case of the ammeter, we have specified the voltage. Now in the case of the voltmeter, we'll specify the current. Suppose it's being traversed by a current I, then we can say the current across a voltmeter is 0. Now everything is exactly the opposite, and not because it is of negligible resistance, since it is of very, so negligible means 0, and this is, it is of very high resistance. So the value of I is equal to 0. Okay, and let me give an example by considering an electric circuit. Suppose that we have a battery, and here we have an electric component D. We don't know the nature of this component. We have a lamp L. Okay, so this circuit is said to be a closed circuit, then it being traversed by a current I. And now suppose that we connect a voltmeter in parallel to D. We know that a voltmeter measures the voltage. We are interested in measuring the voltage across D. So we will connect it in parallel like this. Suppose that this is the COM terminal. Now notice that if this is the point, let me label some points. This is P, this is A, this is B, this is C, and this is N. So the main current I reaches the point A, so we expect that at the node A, the electric current must split into two currents. Suppose that this is IV for the voltmeter and this is ID for the component D. Now we can say apply law. Let me make stuff clearer here. This is the point A, this is the component D, and this is the electric current ID, and this is IV. So apply law of addition. At the node D, so we say that summation of IN is equal to summation of I out. Then on the left hand side of this equation, we'll write the currents that are entering the node, which is given by I, and on the right hand side we'll write the currents that are leaving the node, that are given by ID and IV. And we know that IV, the current corresponding for the voltmeter. So let's say since the voltmeter, since the current, so let me say the current across the voltmeter is 0, since it is of very high resistance. So in this case the value of IV is equal to 0, which is the statement that I have stated here. So in this case I is equal to ID, the value of IV is 0, so I is equal to ID, which means that if you refer back to the electric circuit, so I basically will be equal to ID and the value of IV is 0. So this is exactly as we are saying that this is the battery, as if we are saying that this is the electric component D, this is the lamp, and the lamp is connected back to the negative pole. This is the voltmeter, and this is the COM terminal. So this is the electric current I, and the voltmeter, the connection of the voltmeter to the electric circuit doesn't affect the electric current in any way. So although this is a branch connected to this point, which is the point A, and this is the point B, and this is the point C, but the thing is that across this node, which is the node A, no current leakage will pass through the voltmeter. And let's make the following important statement. Adding or an ammeter to an electric circuit does not affect its different parameters. And by parameters I mean voltage or current. Okay, so adding a voltmeter or an ammeter to an electric circuit doesn't affect its different parameters. So notice that in this case, when we have added the load D6, it affected the parameters of the circuit, so we change all the values of the current. And when we added the ammeter A, nothing have changed. So we added D6 and we proceeded. Then we added an ammeter. When I added the ammeter, we didn't change the fact that I have been increased by 0.5 amperes, simply because the ammeter and the voltmeter doesn't change or doesn't affect the parameters of the electric circuit. And now let's move to section number 7, which is the interpretation of the minus sign. So suppose that here in this case we have an electric component D traversed by a current I from the point A to the point B, and the value of I is given minus 1 ampere, say for example minus 2 amperes. So what does the minus sign means? It reflects the fact that the value of the current I is 2 amperes, so I is equal to 2 amperes, but the direction of the current must be from B to A instead of A to B. So this is exactly equivalent to say that the electric component D, so we don't change the labeling of the branches, we just say this is A, this is B, this is the electric component D, and I in this case is being traversed from B to A with a value of 2 amperes. So we change I from negative to positive, and we change the orientation of the electric current. And now let's move to this exercise, which is exercise number 3. They are telling me redraw on your answer sheet the adjacent figure and determine the direction and the value of the remaining currents I2, I5, I6, I8 in each branch, knowing that. So I will not redraw this on my sheet, and let me start by answering. And the trick in solving such type of exercises is to label the electric current on the electric circuit itself. So the value of I is given by 10 amperes. I1 is equal to 2 amperes. And I3 is equal to 5 amperes. I4 is equal to 3 amperes. And I7 is equal to 2 amperes. And we are interested in determining the value of the remaining currents that are given by I2, I5, I6, and I8. So we are interested in determining I2, I5, I6, and I8. And let me in this case give names for the different nodes. So suppose that this is the node A, this is the node B, and this is the node C, and this is the node D. Notice that with respect to this node and this node, I didn't give any names because simply they are to this node we have two branches. Okay, so no need to apply any law across these nodes. So let me repeat that the unknown currents are given by I2, I5, I6, and I8. Okay, so we have 5 unknowns, and in this case the order that we proceed with is very important. So notice that directly we can notice that we can determine I6 because across the node C we have the currents I1, I3, I4, and I6. The only unknown is given by I6. So let's say apply law of addition of currents at node C. So we say that summation of In is equal to summation of Iout. Now before we start applying the law, notice that the direction of the current I6 is not specified. So we can take it as we wish. Suppose I will take it to be entering the node. So let's suppose that I6 is entering the node. Now if the value of I6 is positive, it means that my choice, the choice of this direction is correct. Otherwise we need to switch the direction. So now we are ready. I repeat that the direction of I6 is not important. We can choose it as we like. And now if the value of I6 is positive, it means that my choice was correct. Otherwise, my choice was wrong, and we need to flip the directions of these currents. So what are the currents that are entering the node C? We have I1, I3, and I6. So I1 plus I3 plus I6, and what are the currents that are leaving the node? Simply they are given by I4, and the only unknown in this equation is given by I6. What's the type of this equation? Linear equation and one unknown. The value of I1 is given by 2, the value of I3 is given by 5, I6 is kept as a variable, and I4 is given by 3. So what's the type of this equation? I repeat, linear equation and one unknown. I6 is given by 3 minus 2 minus 5, so 3 minus 7, which is equal to minus 4 amperes. So what does I6 is equal to minus 4 amperes represent? It means that my direction of choice, the choice of this direction is wrong. We need to switch the direction. So the real direction of the current I6 is given by from C to D, and the value of I6 is given by 4 amperes. Okay. Then we are done with the current I6. Now let's move to the currents I2, I5, and I8. So okay, now we can determine the current I2 either from applying the law of addition of currents at the node A or at the node B. Notice that at the node B we have two unknowns. They are given by I2 and I5. So we'll apply the law of addition of currents at the node A in order to determine I2. So notice that this is I1, which is equal to 2 amperes, and this is also I1, which is equal to 2 amperes, because note that this electric component and this electric component are in series, so they are traversed by the same current according to the law of uniqueness of currents. And before we apply the law of addition of currents, let me choose a direction of I2. Let's suppose that this is the direction, which is out of the node A. So apply law of addition of currents at node A. So we have that summation of I in is equal to summation of I out. On the left hand side of this equation, we'll write the currents that are entering the node, which is given by I. And on the right hand side of this equation, we'll write the currents that are leaving the node that are given by I1, I3, and I2. Knowing that we are interested in determining I2, so the value of I is given by 10, the value of I1 is given by 2, the value of I3 is given by 5, and I2 is kept as a variable. So I2 is equal to 10 minus 2 minus 5, which is equal to 10 minus 7, which is equal to 3 amperes. So I2 is equal to 3 amperes. So I2 is equal to 3 amperes. Notice that this value is positive, which means that my choice initially is correct. And now we are left with the currents I5 and I8. Now I5 can be determined by applying the law of addition of currents at node B. Because it's the only unknown. So we have the summation of I in is equal to summation of I out. Before we apply it and solve, let's indicate a direction of I5. So let me suppose that it is entering the node, although that my intuition tells me that it's leaving the node. So what are the different currents that are entering the node in this case? We have I2, I4, and I5. And the currents that are only leaving the node is given by I7. So this is equal to I7, knowing that you are interested only in determining I5. The value of I2 is given by 3, the value of I4 is given by 3, plus I5, which is equal to I7, which is equal to 2. So I5, what's the type of this equation? Linear equation, unknown, the unknown is I5, which is equal to 2 minus 3 minus 3, which is equal to 2 minus 6, which is equal to minus 4 amperes. So I5 is equal to minus 4 amperes. What does this mean? That the choice of this direction is wrong. It must be away from the out of the node B. And the value of I5 in this case is given by 4 amperes. Now finally we can determine the value of the current I8 by applying the law of addition of currents at node D. This is the node D. And in this case, they already gave me the direction of D, I8 at D, which is out of the node, so no need to specify and interpret. The currents that are entering the node are given by I5 plus I6 plus I7, and the only current that is leaving the node is given by I8. So I8 is given by I5, which is 4. So let me say I5 plus I6 plus I7. So the value of I8 is equal to I5, which is given by 4. I6 is given by 4 and I7 is given by 2, so this is equal to 10 amperes. So I8 is equal to 10 amperes. Now notice that this branch or this circuit represents a portion from an electric circuit. The input of the current is given by 10 amperes and the output of the current is given by 10 amperes. There is no leakage of current, and this is given by the law of addition of currents. So that's it for me this video, guys. In the next part 3, we'll complete explanation of and solving exercises of this chapter.